Good morning, friends. Now, the chapter number 12, Electromagnetic Induction. In this chapter, we can study our new topics is self-inductance. Consider a circuit coil in which the current is changing. It is as shown in figure. The changing current with vary the magnitude of magnetic flux linked with the coil itself, and consequently an electromotive force will be induced in the circuit. The production of induced EMF in the circuit or coil itself on account of a change in current in it is termed as the phenomena of self-inductance. Let's at any instant the value of magnetic flux linked with the circuit itself be phi, corresponding current I in it. It is obvious that phi will be proportional to current I, that is phi is directly proportional to I, or phi is equal to L into I, or L is equal to phi upon I, where L is nothing but to self-inductance or coefficient of self-induction of the coil. The flux linkage for a coil with N, that is the number of turns corresponding to current I, will be written as N phi B is directly proportional to I, N phi B is equal to Li. Here the self-inductance L is equal to N phi B upon I. According to Faraday's law, the induced EMF E is given by, we know E is equal to minus d phi by dt. Here E is equal to minus d, we can put the value of phi. Phi is nothing but Li. Therefore d in brackets Li upon dt. Therefore we can get the equation E is equal to minus L di upon dt. Now the unit of inductance. The unit of L is equal to mod of E upon mod of di upon dt. Therefore E is nothing but in voltage, we can measure, upon current it is measured in ampere, and time in measure in second. Therefore we can get voltage upon ampere per second is nothing but to the Henry. The unit of inductance is Henry. The definition of L is nothing but to the first case from phi is equal to L into I, or L is equal to phi upon I. The self-inductance of a circuit is the ratio of magnetic flux linked with the circuit to the current which is flowing in it, or the magnetic flux produced per unit current in the circuit is defined as its self-inductance. Now in second, by using L is equal to, that is mod of E upon mod of di upon dt, that is we can write down also L is equal to minus in brackets of E upon di upon dt. The self-inductance of a circuit is the ratio of induced electromotive force produced around the circuit to the rate of change of current in it. or we can state the induced electromotive force produced around the circuit per unit rate of change of current in it. It is defined as the self-inductance of the circuit. When a current is increasing in the circuit, an induced EMF acts as opposite to it. Consequently, the work will have to be done in order to establish the magnetic flux associated with a steady current I0 in the circuit. The work done in the time dt is dw is equal to E dot I dt. Now the small work done dw is equal to E dot I dt. Therefore dw is equal to, we have put the value of E minus E di upon dt into I dt. Therefore dw is equal to minus L I di. Here dt gets cancelled. Then the total work W is nothing but integrations of dw. Therefore the integrations of 0 to I0 minus Li di. Therefore we can get the value W is equal to minus L, that is self inductant. It is common outside the integrations, integration of 0 to I0 I di. Therefore work done W is equal to minus L I0 square upon 2. Then the work should be done here. W is equal to 1/2 L I square 0. Here minus sign, it should be take out here by using in magnitude. W is equal to 1/2 L I square 0. Now if I0 is equal to 1 and W is equal to L upon 2, that is L is equal to twice of work, that is W, 2W. Hence self-inductance of a circuit is numerically equal to twice the work done in establishing the magnetic flux associated with unit current in the circuit. This work done W will represent the energy of the circuit. Now the energy of the circuit is equal to 1/2 Li square. Comparing the equations of kinetic energy is equal to 1/2 mv square and E is equal to 1/2 L I0 square, we can find the self-inductance L of an electric circuit plays the same role, that is electrical inertia in mechanical motion. This is self-inductance. Now next are inductance of a solenoid. If a current I is established in the winding of a long solenoid, the current produces a magnetic flux phi V through the central region. The inductance of solenoid is given by L is equal to N phi B upon I. Now here N is the number of turns, N phi B is equal to magnetic flux linkage. For a length L, near the middle of the solenoid, the flux link is N5B is equal to NL into vector B dot A in brackets. Therefore, we have get the equation NLBA for the theta's value should be 0. When N is the number of turns per unit length, B is nothing but to the magnetic field inside the solenoid. A is nothing but to the cross-sectional area of the solenoid. We know the magnetic field inside the solenoid is given by B is equal to mu 0 Ni. Hence, L is equal to N phi B upon I. Now here put the value of N phi B is equal to NL BA upon I. Therefore, NL we can put the value of BA is mu 0 Ni upon I. Therefore, we can get L is equal to mu 0 N square L into A. Here AL is equal to V, that is interior volume of the solenoid. The inductance per unit length near the middle of the long solenoid is L upon small l is equal to mu 0 N square into A. Then capital L upon small l is equal to mu 0 N square. Now the area's value we have put in brackets of pi d square upon 4. Now where d is the diameter of the solenoid, this implies that inductance of a solenoid is L is directly proportional to N square and L is directly proportional to the D square. Hence, L is equal to mu 0. It is multiplied by the quantity with dimension of length. Then mu 0 is expressed as Henry per meter if the inductance in series or parallel. If several inductance are connected parallel, then the total inductance is determined by using following relation. For inductance in series combination, L total is equal to L1 plus L2 plus L3 up to Ln. Now the inductance in parallel combinations, therefore 1 upon L total is equal to 1 upon L1 plus 1 upon L2 plus 1 upon L3 up to 1 upon Ln. Now next, energy stored in magnetic field. Changing the magnetic flux in a coil cause an induced electromotive force. The induced electromotive force so produces oppose the change and hence the energy has to be spent to overcome it to build up the magnetic field. This energy may be recovered as heat in a resistance of the circuit. The energy spent to build up a current I in a circuit having an inductance is L. Therefore, we have get E is equal to minus L di upon dt. The work along in moving a charge dq against the electromotive force is dW is equal to minus E dQ. Therefore dW is equal to, we have put the value of E, L di upon dt into dq. Therefore dW is equal to L di dq into there upon gt. Therefore dW is equal to Li di. dq upon dt is nothing but to the currents, definition of current. Then therefore the total work done which is carried out there, therefore W is equal to integrations of dW. Therefore we have get integration of 0 to I Li di. Therefore work W is equal to 1/2 Li square. Therefore for the energy UB is analogous, UB is equal to 1/2 Li square. This is the energy store, that is UB, in magnetic field and is analogous to the energy storage, that is the total electrostatic energy UE is equal to 1/2 CV square in electric field in a capacitor. It can be shows that this energy stored up in magnetic field per unit volume comes out to be, in brackets of its value, 1/2 mu 0 B square. It is in joules, which is parallel to, in brackets of 1/2 epsilon 0 E square, the energy density UE in an electric field of E. Therefore mu 0 and epsilon 0 being the permeability and permittivity of free space. This is the energy stored in magnetic field.